Alrighty, so in lesson 8.3, we're going to really start to put everything together. In lesson 8.1, we used simulation to decide whether or not Mrs. Manuel was exaggerating about her free throw percentage. However, all the classes had found slightly different p-values. Some were statistically significant, sometimes they were not. So how can we find the true p-value so that we make the correct conclusion? We won't be typically using simulation for that. We'll calculate that more paper pencil style. So we're going to have to set things up. We're going to carry out the significance test formally from lesson 8.1, this time by writing things out. The hypotheses to start. So our null hypothesis, we assume innocence until proven guilty. So I am 8, oh my goodness, that is not 0.80. Let's make that one an 8. 8, 0. Hopefully you guys can read that at home. 80% successful at making my free throw shots. And we had some evidence that suggested maybe I was not so good. So the true proportion of made shots by me was less than 0.80. Now my parameter would be P, the true proportion of made free throws. Okay, so in two-part A, each class found a different p-value because each dot plot was slightly different. So would it be appropriate to use a normal distribution to model the sampling distribution of p hat? This goes back a few sections for us when we talked about sampling distributions. So we have a condition to check for this. Is it normal, or would it be appropriate to use a normal distribution here? If our percents meet, our sampling distribution meets the large counts condition. Well, the large counts condition says that you take your sample times the proportion and the sample times the complement of that, and do you get at least a count of 10 for each. Now we are operating under the assumption that I am 80% successful. So if I take 50 shots, there's my sample size, and I truly am 80% successful, how many shots would I typically expect to be making? 80% of 50 would make 40. That is at least 10, so we meet the large counts for that piece, but we have to check the other. So the percent that I would miss, if I make 80%, I would be expecting to miss on average 20%. 20% of 50 is 10 exactly. Boy, we just snuck in there on that count. Yes, because our counts meet the large counts condition of getting 10 for each, it would be appropriate to use a normal distribution. Great news. Are there any other conditions that we should check here? Well, we talked about with confidence intervals before. It's always important that we have a random sample. If our sample is not random, and they usually will tell us that somehow, it does not necessarily represent the population from which it came from. So we definitely need to make sure that is the case. It does say, we assume that I took 50 random free throws. There was nothing special about it. So yeah, we could assume that was met. Okay, what else? Now that the conditions have been met, let's calculate the mean and standard deviation of the sampling distribution of our sample percentages. So the average value, the mean of all proportions, in other words, our null hypothesis, is 0.80. The standard deviation is 0.80 times 1 minus 0.80, or 0.20, divide by 50, square root. So there's our standard deviation of our sampling distribution, 0.057. So what that tells us, if we interpret that, it's been a little while maybe to interpret standard deviation, but we could say that, oh, I should put my little notation there. We should say that our samples of 50 will typically vary by about 5.7% from our average of 80% made free throws. Typical variation from the mean. Use the mean and standard deviation you found to label the normal curve. So we said that normal fits from our large counts condition. Our mean would be here right in the middle at 0.80. One standard deviation, so adding that gets us 0.857. Adding it again, 0.914, and a third standard deviation out, 0.971. Now if we go the other way, subtract, we have 0.743. Subtract the standard deviation again, 0.686, and one more time, 0.629. These are the percentages we expect to see. If you think of our empirical rule, 99.7% of the time, we would expect values to fall within these two percentages. How many standard deviations below the mean is 0.64? Well, let's label where that is. 0.64 would be somewhere, I'll almost estimate, maybe about here. This is our p-hat value, our 0.64. We actually are going to call this our test statistic. Based on the sample, this is where our data value falls. So how many standard deviations below the mean is that? Well, our good old z-score formula is helpful for that. 0.64, what we observed, minus 0.80 is how far in percentages below the mean it actually falls. Divide by the standard deviation, now we know how many standard deviations below, and we're going to get negative 2.81. So if we have an 80% free throw shooter and they only make 64% of their 50 shots, how unusual is that? Well, that outcome is negative 2.81 standard deviations below the mean. The probability of that outcome, we could use table A, our normal distribution table for that, and look for our z-score of negative 2.81. The area to the left of that z-score represents the percent of times we would expect that outcome or less to occur, and the area from the table is 0.002, roughly. So that right there is really our p-value. The probability of obtaining a sample at least as unusual as we did purely by chance. What conclusion can we make? Well, since, and I'll tell you what, instead of me rewriting it, let me just slide this paper in here, which has my final answer on it. Since the p-value of 0.002 is less than our 5% cutoff for our significance level, we reject the null. And we have convincing evidence that the true percent Mrs. Manuel makes is less than 80%. Spoiler alert, I could have told you that from the beginning. In fact, if I made 64% of my free throws, I would consider that a lucky day. I am just not that good. But now we have it on paper. Not through a simulation, but through statistical calculations, putting together things we've talked about before, checking a couple of conditions, calculating how unusual an outcome is by getting the z-score and finding the probability that goes along with that particular z-score.